is Williamson ether synthesis. Got it? So you get one alkoxide and you take alkyl halide. Alkoxide goes and join itself to the alkyl halide. That is SN2 reaction. Okay. So whomsoever is alkyl halide, so be careful that the alkyl halide should not be touched like this. That we have seen. It should not be aryl halide because of the partial double bond character. Reaction will not happen. As you can see here, got it. Other thing which we have seen as when you have ether, you can react with HI, it will break. Okay. If it is SN2, I minus will attach itself to the smaller alkyl group. Got it. Reaction with HX or HI. HI is the most reactive. So we use mostly HI for the reaction. If it is SN2 reaction, the I minus will attach itself to the smaller alkyl. The I minus is going to be attached to the smaller alkyl group CH3I, and oxygen will go with the bigger alkyl. But if it is SN1, then you will look for the stability of cation. For example, tertiary. Cations are very stable. So tertiary cation will form and I minus will attach onto the tertiary. That's what we have discussed. We have seen, we have just started with the reaction of anazole. Okay. In anazole, basically, we need to, before starting the reactions, we need to look at the structure, benzene structure, how the electron density is being distributed on the anazole. That we need to look at. Got it? Once we have the idea of the electron density of the benzene ring, we can easily make out the where the reaction is going to happen. Okay. So just let me quickly start with the reactions of anazole, right? That we need to look at in the last class, right? So this is the only thing which is pending. Because rest everything is completed in this chapter. Just a second. Let me start the camera also. Okay. So we have anazole and okay, great. So now all of you can see it very clearly. Yeah, anazole, is there any doubt related to the resonance structures of anazole? The lone pair of oxygen is there. And that lone pair get into the benzene ring. It makes the benzene ring more electron rich. Got it? So, but where the resonance effect is coming, Aisha? Where the resonance effect is coming? Of the OCH3 group. It is coming at ortho and para positions only. Got it?
Yes.
Marwa, is it clear? Why am I telling? Why Aisha is telling that the resonance structure, resonance effect is affecting the ortho and para positions? What's the reason behind it? Can you tell me? So, what's the reason behind it? The reason you can see very clearly that the minus charge is going to come at ortho and para position. Just remember that the resonance effect is going to appear at ortho and para positions in the benzene ring. Is it clear or not? So this is the position Jaslene, which is more electron rich. Okay, ortho positions, both the ortho positions have the negative charge and the para position. So this I hope is clear to everybody. Okay, now we can start the reactions of anisole. What is the name of this reaction? Tell me. Jaslene, can you see the reaction? Marwa, Aisha, can you see the reaction? What is the name of this reaction? And what this reaction try to do on the benzene ring? That we need to figure out. Got it?
So is this Fiddlecraft alkylation?
Yeah, Fiddlecraft alkylation. This so it is Fiddlecraft alkylation. The negative charge is coming at the ortho and para positions. You can see from the above. And this CH3Cl and AlCl3. AlCl3 will act as a Lewis acid. It will remove the Cl minus and will become AlCl4 minus. Okay, it will abstract the Cl, leaving behind CH3 plus. So where the CH3 plus is going to attach itself, you can see on the benzene ring. The ortho and para positions, the negative charge is passing from the ortho and para positions, okay, not from the matter. And the CH3 plus can come and join itself on the ortho and para. OCH3 was already there, okay, that was the group. So this OCH3 is ortho para directing group. Is it clear or not? Jaslene, Marwa, Aisha. So Aisha has already answered, yeah.
Yes, okay.
This is Fiddlecraft's right alkylation. Okay. Suppose instead of alkyl group, if you want to attach acyl group. So what is acyl? That becomes Fiddlecraft acylation. Everything remains same. But instead of alkyl group, we have the acyl group. Right? So what is acyl group? First we need to figure out. It looks like the similar, very similar reaction with a similar reagent. And the name is slightly different, okay? Instead of alkylation, you have acylation, Fiddlecraft acylation. Okay, so this you are going to attach the acyl group, right? That is CH3COCl. So you need to remove the H and Cl, and to get these two groups joined together, you need to take a catalyst. The catalyst is same AlCl3. That will remove the Cl minus, okay, and leaving behind CH3CO plus and AlCl4. Got it? So where this plus is going to attach itself, Marwa, am I audible or not? Jasleen, I hope I'm audible to all of you, right? So where this CH3CO plus, this is known as acyl group, okay? Where it is going to get attached on the ortho and yeah, para position. Got it? Yes, exactly, Jasleen. Ortho and para. Yes, ortho and para are going to get affected by the rhythms. Yeah, okay, no problem. Jasleen. So, but I hope the reaction is clear. Okay. Plus para I can draw. So I hope it is clear to all of you now. Let's talk about another reaction, but this group is a very big group. Okay. So if it is a very large group, it will be more difficult for it to get attached on the ortho, because ortho being near to the main group, being adjacent to the main group, uh, it is historically hindered, right? Means it is crowded. So this para product is going to be the major product which is formed in large amount. So this I hope is clear to all of you, right? So let's do another question. Another reaction, and this reaction is the nitration. So how you do the nitration of benzene, and what do you mean by nitration? Which group are we going to attach? If you are trying to put the NO2 group, yeah. So that is done by taking HNO3. Nitration can be carried out by taking HNO3 along with H2SO. What is the role of H2SO4?
So acts as a region.
Yeah, it actually HNO3 you need to yes, exactly. This is acting as a catalyst and it removes the OH. By protonating it, it removes the OH as water. H2SO4 is a very good reagent which can absorb water. And you will have NO2 plus group left on this, left behind. This NO2 plus group, and as we know from the resonance structure, so this is going to lead to the formation of a reactive intermediate known as nitronium ion. H2SO4 removes the water, okay, from HNO3. H2SO4 everywhere we have seen, in the alcohols also we have seen, that causes dehydration. Okay, of alcohols it removes water. This NO2 group, where it will get attached on the OCH3, you can see that the minor charge density is passing through ortho position and the para position. Okay, and this NO2 plus is going to come and join itself Because plus will be very it will be very easy for the plus to join itself to the position where the negative charge density is moved. So ortho para positions you have minus charge. So NO2 is going to come and join itself to the ortho and para position. Got it? So this I hope is clear to all of you. Okay, this is nitration, ortho para directing group. Got it? So let's do some more problem. This problem is from your all the chapters, right? All the chapters of which we have studied of organic chemistry. That is haloalkane, haloarine, and then we have alcohol, phenol, and ether. Okay. So you need to tell me the reagent. So Aisha, Marwa, Jasleen, just all of you can try.
So chlorine and Lewis acid.
Yes, chlorine and Lewis acid, not chlorine and HNO. Okay. Photohalogenation is used for alkanes. Okay, for benzene, yes, exactly. You use chlorine, and either you can write Fe or you can write FeCl, or you can write AlCl3, some Lewis acid catalyst. Though there are a lot of other Lewis acid catalysts like SbCl5, SnCl4, okay, ZnCl2. Okay, they are less commonly used. These are the two. If you take Fe, that reacts with the chlorine and forms FeCl. That is one and the same thing, right? Is it clear? Now we have seen how to convert what should be the reagent. What are we doing? We are attaching NO2 group, okay? And the reagent just now we have seen about this reaction. This is nitration. But when you are writing in your CBSE examination, you should write it like this: HNO3, H2SO4, heat. But that will bring the NO2 at ortho and para position. Okay. So next is separation, because you need to separate ortho and para position. Separation by distillation, you can write. Okay. The ortho will have lower boiling point, the para will have higher boiling. Separation by distillation. So you will get the para. How you are going to get? This also we have seen. So what should be the reagent? Marwa, Jasleen, tell me. Aisha.
Sir,
You are replacing the Cl by OH. So what reagent do we need to take? NaOH, right? This is
Yes.
bimolecular nucleophilic Dawes process, but you need to take because this is not an easy process. Okay, because you know that Cl has partial double bond character. So what you need to do over here is you need to take high temperature and pressure. Heat 170 degree Celsius and pressure. Okay, that will cause the OH minus to come and take the place of Cl. Because it is a basic medium, so you will have the O minus. So because you need to get OH, so just put H plus also as a mean to do the protonation, okay, acidification. Because you have taken the basic medium. There you will get the O minus Na plus. Okay, make it O to make it OH, take H plus. Okay. So this is Dawes process which we have seen earlier. Okay. I hope this is clear to all of you. Okay. This is not taught yet, but very quickly we are going to start with this amines and all. So this is tin and HCl or Fe and HCl. These are the metal and acids are the reducing agents. The metal is going to give the electrons and the H plus is giving H. So that NO2 will change to NH2. Is it clear to all of you? Reduction of nitrobenzene. I hope all of you are clear with it. Got it? Then this is reduction. Then other steps you are familiar with it. Okay, in from the chapter of haloalkane and haloarene. I take NaNO2 and HCl by maintaining low temperature between 0 to 5 degrees Celsius. What will happen? I keep the temperature low as of now. So what will happen? Aisha, Marwa, Jesslyn, tell me. Why we have kept the temperature low? What's the reason? Maybe something may be forming that can break, okay, that can react, that can get spoiled with the high temperature. That's why we have kept the low temperature, right? So what is that thing? It must be a reactive intermediate compound that may not be very stable. Is it clear or not?
Yes, sir.
So that is, so what is this reaction? Tell me quickly what this NH2 will get converted to. This is related to NH2. I will give you a hint. This NaNO2 and HCl are also written as HNO2, nitrous acid.
Sir, diazone.
Yes, it is diazonium. Got it. And then in the next step, that can be converted to any desired compound. What I need to take over here? To get it reduced or to get it converted to Cl, or if I put Cl, I can put Cl also. So tell me.
So NaNO.
Yes, NaNO2 and HCl we have taken. So in the previous chapter, we have seen either we have the Getterman method or the Sandmeyer. Okay, if you want to convert it into halogen, Getterman use copper powder and HCl. As Sandmeyer uses CuCl and HCl. Got it? So that you can check it very easy. Okay, but you need to remember this is Getterman method. Sandmeyer was this. You need to heat it also because that will N2 will break. Is it clear to all of you? Any doubts on this? What about this one? Tell me. The last one. Any idea about it? NUH CH3I. Got it? What will it be?
So parachloroanisole.
Yes. So this is first of all NUH ONA will form. Got it? This will form. This is Williamson ether synthesis, right?
Yes.
First, we will end up with ONA. And then this CH3I, it will displace the iodine and OCH3. Parachloroanisole, right? Exactly. So this I hope is clear to all of you. Okay. So let me start with the other chapter, that is of coordination compounds. So first of all, we need to start with the classification of the coordination compounds. Got it? And we need to look at what they are and how they are prepared, how to name them, what type of isomers they can show. Okay, whole lot of things. Okay, basically these are mostly related to D block elements. Okay, they are found by transition methods. So first of all, we have double salts We have addition or molecular compound. Addition compound or molecular cell. Well, out of those two categories, we have two subcategories, double salts, and the other category is coordination compounds. So what's the difference and what's the similarity between addition compound or molecular compound? What are they? And they are divided into two categories, double salts and coordination compounds. So any idea? What are they basically? Double salts or addition compound. Okay. They are all formed when two or more than two compounds are joined together in a fixed ratio. Got it? So when two or more than two compounds join together in a fixed ratio, then the compound which you get is known as addition compound. Got it? Is it clear?
Yes.
So the name is indicating addition compound. So Marwa, Justin, what are addition compound? I think I joined the wrong meeting. Yeah. So what are addition compound? How will you define them? Then we will start with the examples. Tell me quickly.
Sir, two compounds which are in a fixed ratio.
Yeah, they are formed when the two or more than two compounds join together in a fixed stoichiometric proportion. Okay, they are addition compound or the molecular solids. Can you give some examples of these compounds? Any example? We use potash alum. Got it. So potash alum, you might have seen it. It is used in our home also. It's some places. K2SO4. It is formed when potassium sulfate, aluminium sulfate are mixed together. You get a potash alum whose formula is A2SO4 dot got it. Is it clear?
Yes, sir.
So this is potash alum, and you can see that 1 mole of aluminum sulfate, potassium sulfate, and they are joined together. Got it? You might have in your school lab, you might have used more salt in class 11th or maybe class 12th also. More salt. So what's the formula of the more salt and why are we studying it here? Any idea? More salt.
So is it used in titration experiment?
Yes, it is used in titration experiment. Exactly. Yeah. So it is used in titration experiment. That's true. So basically, what is more salt basically? It is made up of it has iron in it. Okay. It is ferrous ammonium sulfate. Okay. So you use FeSO4 and ammonium sulfate and 6-2. This is more salt. So I hope this is clear. This is also what type of compound is it? Is it a double salt? First of all, it is an addition compound. Got it? Further, we will look into the double salts and the coordination compound. We will look into that, right? So first and the foremost thing that should be clear, very clear to you, that is, it is an addition compound. Is it clear to all of you? Addition compound. So, Marwa, why it is an addition compound? Can you tell me quickly? Yeah, Marwa, am I audible?
Yes, sir.
Yeah, so why it is an addition compound? Why should I consider it as an addition compound or a molecule solid? Because how it is formed? It is formed when the two or more than two compounds join together in a fixed ratio. Okay, you can see that 1 mole of FeSO4, 1 mole of Fe ammonium sulfate, and 6 moles of water have joined together. Okay, to give you more salt. Okay, you need to write the definitions very clearly, Marwa, right? Got it? So, Aisha, Jaslene, is it clear?
Yes,
This
sir.
is used in titration with KMnO4. That is true because FeSO4 get oxidized to Fe plus 3 with KMnO4. Yeah, that's the use. It has miscellaneous uses more salt, right? But the thing is that it is basically formed by mixing together two or more than two compound. That is the most important thing. That is why it is known as addition compound or molecular solid. Okay. Let me write one more addition compound. All of you must have seen at some point of time. You might have studied in your class 10th also. Got it. So copper sulfate solid anhydrous. Anhydrous means it is without water. It doesn't have water in it. Okay, that is white color. And when you add water, 5 moles of water, what happens? it become blue color. Got it? Is it clear?
Yes, sir.
And nickel chloride, there are many compounds like this. Okay. Not only with water, with NH3 and all, we can have a lot of compounds behaving in a similar pattern where they are formed when two or more than two compounds are mixed together. So these are the two compounds, they are mixed together, and that's why they're addition compounds. Got it? And they are classified into two different categories. Right? Two different categories, and they are double salts and coordination compounds. What's the difference? If you put this potash element back to water, so Jaslin, what may happen? If you try to dissolve the potash alum into water, what all ions are we going to get? This is SO4, right? So all of these ions, these double salts, split completely into the ions. So you will have potassium, you will have aluminum ion, and you will have sulfate ion. Not it. And where does the water goes? That get dissolved in the water itself, right? That get mixed up with the water. Is it clear or not? So these are double salts. And the main feature of the double salt is that they completely split into their ions when dissolved into water. Are you getting that? They completely split into their ion constituent ions. You can see here. It is going to give the test of potassium, aluminum, sulfate, got it? Because they are splitted completely. So what all ions more salt is going to give, Marwa, upon dissolution in water? Can you tell me? Marwa, can you tell me? Am I audible? Suppose if you take more salt and if you dissolve it in water, what all ions you will be having in the water? You will have Fe2 plus ion, you will have sulfate ions, you will have ammonium ions, sulfate already are taken, got it? And water will mix with the water only. That will not be an ion. So it will completely split into ion and it will completely lose its identity. Is it clear or not? So how will you define? Marwa, Jasleen, Aisha, what are double salts? Can you quickly tell a definition for double salts? Tell me quickly.
So it's like a substance when dissolved in water, it dissolves into ions.
It
Like
is an addition compound, okay? Yeah, exactly. So which is made up of two or more than two compounds. And exactly when you put it in water, so it is an addition compound. Okay. That also we must say. And when we put it in water, it splits completely into ions and it loses its identity. Okay, you don't know what it was. If I give you the aqueous solution, you will not be able to make out what it was before, right? You because all the ions will be split apart. Okay. And these are so this the definition is clear, I hope. Aisha, Jaslene, Marwa. Now I need to talk about the coordination compound, which is the main the chapter is based on this. Okay. There is one more way to write them. By using square brackets. Why we use a square bracket, that will also be clear in a while. This can be written as Ag with three NH3 molecules along with the Ag put into square bracket and Cl minus outside the square bracket. Okay. So what happened with these coordination compounds? When you put them in water, they don't lose their identity completely. They don't get dissociated into the original ions. They don't get completely dissociated. Is it clear? So suppose if you are putting it in water, if you are doing the dissolution, it is going to break, but some part of it is going to remain as it is. Is it clear or not? So has it broken completely into Ag plus ammonia and Cl minus, or only a part of it is separated out and the remaining is still intact, right? So that is the only difference between the coordination compounds and the double salts. The double salts split completely, while the coordination compounds, they retain their identity. coordination compound do not break completely into their constituent ions like the double salts. Is it clear? Got it?
Yes.
Okay. So this is the basic class of difference between the coordination compounds and the double salts. Double salts split completely. Coordination compound do not completely split. They still retain their part of their identity. Okay, for example, if I take this, if I put it into water, this Ni nickel H2O6 2 plus and Cl minus. Got it? So that part is the part of the thing which is there in the square bracket that is still intact. That is not separated completely into ions. Okay. Now these coordination compounds are also known as complexes, which is the other name for the coordination compounds. Coordination compound or complexes. There can be complexes can be perfect or imperfect. That depends upon, though we have said overall that they do not break into their constituent ions. But if we look at them closely, there are some of them which may slightly break into their constituent ions, while there are some other of them which do not break at all, which are very stable. Okay, so the perfect complexes are those complexes only which are absolutely perfect, which do not break into ions, or their splitting into their constituent ions is negligible, which cannot be detected by experiment. On the other hand, these imperfect complexes, they up to some extent, okay, I'm not telling that they are double salts, okay, because double salts completely split, okay, they up to some extent, they split into the ions, okay, up to some extent, okay. Perfect complexes have high formation constant, okay. So perfect complexes have high formation constant, okay. That means they are very stable and they can, formation constant is the equilibrium constant, right? Its higher value indicate that they will have tendency to form. Is it clear? So these perfect complexes, as the name indicate, they are very stable and they are they have high formation constant value. Means their equilibrium constant for the formation is very high. Imperfect complexes are, these were very stable. these are not so stable, and they have low formation constant. Okay. Equilibrium constant for the formation is low. Got it? Is it clear or not? Got it? Any doubts?
So what's high formation constant?
High formation constant means it is an equilibrium constant. You might have studied equilibrium in class 11th. Okay. So when you take two things, they form, and they have some equilibrium constant value. High value indicate more products are being formed, and low value indicates less products are being formed. High formation constant means they are very stable. I will give you the examples also in the later part of the chapter. So just you can recall equilibrium constant. We have seen it in that Nernst equation also, right? Nernst equation, we have seen that LNQ reaction quotient equilibrium constant. Okay, that tells us whether the thing is stable or not. Okay, by what extent the reaction is happening. Is it clear? So imperfect
Yes.
complexes, basically they actually the perfect will remain associated up to a large extent. Okay, they will not break at all. And imperfect can break a little bit into their ends. Okay. But doesn't mean that imperfect are double solved. Double solved actually they completely split. Okay. Imperfect up to some extent they can slightly break. Okay. Is it clear?
Yes.
So formation constant I can tell you, and this is just for example, nickel, you have taken nickel 2 plus, and you take 6 NH3 molecules, and these NH3 molecules combine with the nickel NiNH3 whole 6. Okay, because ammonia do not carry any charge, they were neutral, so plus 2. Got it? It will have plus 2. So what the equilibrium constant will be the concentration of the products divided by the concentration of the reactants. Got it? Each raised to the power its coefficient. This is the equilibrium constant. And because it is representing the formation, in this case it is called formation constant. Its high value means this is very high and the concentration of these two are very low. All of them are consumed. Okay, and all of them have combined to form the product because the product is very stable. So again, it means it is very stable. Got it? I hope this is clear to all of you. Marwa, Aisha, Jasleen. Okay. So
Yes, sir.
imperfect complex slightly it will break, and you can make the ions react with some other ions because they are slightly splitting and getting separated. So you can suppose if you take CD, let's take this one, and if you put H2S is gas, you might have used it in your salt analysis in the school practicals. So H2S, actually this is a complex. Ideally it should not break, okay. But with H2S it can split, and the cadmium will form cadmium sulfide, which is a yellow precipitate. And 4Cn minus get separated. Got it. And 2H plus. I will take a similar complex of copper. Having cyanide ions, copper plus 1, and I pass H2S gas through it. No change or no precipitate of Cu2S is observed. On the other hand, there we saw precipitate of cadmium sulfide. So what is happening basically? Why that cadmium sulfide was forming and this is not forming? Cu2S is not forming. What's the problem? The problem is that cadmium sulfide was not very stable, so it was able to break apart and react with H2S. Okay, so that was imperfect complex. Got it? And CuCN4 3 minus was very stable, very perfect, right? And so it was not able to break apart. Is it clear or not? The meaning of perfect and imperfect complex. Aisha, Marwa, tell me quickly. Jaslene, is it clear?
So the copper ions won't.
Yeah, they are actually more tightly bound to the cyanide. They have high formation constant. That's what it means. It is a perfect complex. Got it?
Yes.
Because they are perfect, perfect means it is highly stable. So the chances of splitting into its constituent ions are very low and you will not be able to separate them, right? But in that case, in CDCN4 2 minus, it was imperfect. But how you know? We can't see the ions and whether they are getting separated out or not. So what we do, we put some reagent, H2S. And H2S actually was able to react with cadmium, and we are able to see it clearly because that cadmium sulfide is yellow colored PPT. So we can immediately find out that, okay, this cadmium sulfide is forming, yellow colored PPT is there, right? Is it clear? So
Yes, sir.
that was imperfect, and this copper one was perfect. Okay. So this is the basic classification. I hope just you can take the uh, picture of it so that you can revise. Addition of molecular compound. There are two types: double salts coordination. Addition compounds are formed when two or more than two compounds join together in a fixed ratio. Okay. And if they completely split into their constituent ion, they're double salts. And if they don't split completely, they retain their identity, they are coordination compounds. The part of it which is not splitting, we represent it in a square bracket. Coordination compound can be further classified into perfect and imperfect complexes. Perfect complexes are those which are very, very stable and which do not split at all into their constituent ions, and while the imperfect complexes can split apart up to some extent, not as not like your double salts. Okay, up to some extent they can split. They're not very stable. Right. So this is all what we have seen. Now the next is some common terms and terminologies which are used in coordination compounds. So we have seen coordination compounds and a lot of things. We have seen basic criteria, definitions, and all. Now, how do you represent what that square bracket mean and what it is? Okay. So, for example, I will write one coordination compound. As an example, and with that, I will tell you uh, what these different representations mean. This part is known as coordination sphere or coordination entity. Is it clear? Coordination sphere or coordination entity. So what it includes? It includes a central metal atom or ion and its ligands. These are known as ligands. So let me tell you what are these central metal atom or ion. The so what is coordination sphere or entity? You can write the definition I am dictating. Coordination sphere or entity is basically the everything which is included in the square bracket. Got it? Is it clear? So within the square bracket, what all things you have? Aisha, Marwa, tell me, Jasleen, tell me, what all things you have in the square bracket? I have written them above and below.
So central metal and a ligand.
Yeah, central metal atom, exactly. It is a central metal atom or an ion. Okay. And the ligands. Ligands are groups which are connected to the metal atom. Okay. And the whole thing is enclosed in a square bracket. And that is known as coordination sphere or entity. I hope this is clear. The outside part is known as ionization sphere. And as the name indicates, it consists of ions which can ionize. Got it? So what do you mean by that? So it consists of ionizable ions. Is it clear? Means when you put it in water, the coordination is sphere and the ionizable ion, two chloride ions will separate out. Got it? Okay. So let me. So what is the definition? Coordination is sphere entity. It is everything which is retained in the square bracket. It includes the metal ion and the ligands. Ionization sphere consists of ionizable ions which can separate when put into water. So when a coordination complex is put into water, only the ionizable part present outside the square bracket that gets separated out. Is it clear or not? Any doubts on this? Coordination sphere entity or ionization sphere? Let me explain some more details about the central metal atom or ion. It could be from other block of the periodic table also. Generally, it is transition metal, right?
So they're all metals. The central
Mostly they are metals. Yeah. Mostly metals and mostly they are from the D block, but smaller ions like magnesium. Magnesium we see they call complex, that chlorophyll part. Okay. That is the complex. Hemoglobin, that iron is complex. That is the complex of iron, right? So most of them are metals, right? Because non-metal will have a tendency more to undergo different types of bondings, right? So generally they are metal atoms or ions. Okay, mostly commonly from D block and which have vacant orbitals in which so it can accept. Got it? So is it clear what is central metal atom or an ion? It is a metal atom or ion generally from D block, which has vacant orbitals in which it can accept the lone pair donated by the ligand. So lone pair basically, and that's how the metal and the ligands combine together. Is it clear? So you can
Yes.
see the nickel is the central metal atom. In this case, cadmium was the central metal atom. Nickel is the central metal atom. Copper is the central metal atom or ion, right? And silver is the central metal atom or ion in this copper and the nickel. So mean that is the heart of the complex, and it must possess vacant orbitals, okay, in which it can accept the lone pairs donated by the ligands. Got it? Now come to the ligands. So what are they? What are these ligands? They can be neutral molecules or ions. Which can donate one or more than one pair of electrons, means lone pairs or pi electron. To a central metal atom or ion. Is that clear?
Sir, is chlorine a ligand?
Yeah. Cl minus is a better than Cl2. Okay? Minus can donate more easily. NH3. Normally we write it like this. We put an arrow, okay, from the ligand to metal, representing donation of pair of electron from ligand to metal, and metal is acting as an acceptor. It is accepting electron in its vacant orbitals. Okay, we need to check from the electronic configuration what all orbitals are empty in it. Okay, and where the metal can accommodate the lone pairs, which are given by the ligands. So this is the central metal atom, and this is a ligand. Ligands can be positively charged. They are less common. Positively charged are very less in number because they need to give electrons. So they are mostly negatively charged or neutral molecules, okay, which have a pair of electron in the form of a lone pair or pi electrons, which they can share with some metal atom. So these are the ligands. Got it? So I hope the definition of the central metal atom and the ligands is clear. You can see it, check it, and let me know if anything is not clear. Very basic thing. It's very easy. Okay. So, but you need to listen carefully, and you can, once you listen, you can just on your own, you will be able to write all the definitions once you have it in your mind. The idea of the terms are very clear in this. Okay. Ligands, central metal atom or ion. The next part is there are some other things also. We have seen ionization sphere. Ionization sphere consists of ionizable ions, right? They get separated. Okay. So if you put this complex into water, it will give two Cl minus chloride ions, Cl minus ions into water. Okay. Because those are present outside the square bracket in the that part is known as ionization sphere. So whatever is present outside the square bracket, that get ionized on putting in water. This I hope is clear to all of you. Any doubts on this? Desleen, Marwa? So now the next part is coordination number. There is one more thing which is not we are not able to see in this formula, but we will be able to see when we write the complete structure, detailed structure. So this coordination number is the total number of coordinate bonds between the metal and its ligand. Very simple. From the definition, also you can make out number of bonds between whom. Is the definition to clear to all of you? Marwa, Jasleen, Aisha.
Yes, sir.
So suppose you need to count the bonds in the structure. And I am writing in a very general way by representing metal as M. So can you tell me what are the coordination numbers from left to right? For this one, I will write it in an abbreviated manner. What is the coordination number of this complex? There will be some ligands, right? I've not written it. Is it clear?
Yes, sir.
So what is the coordination number?
2.
Yes, exactly. That's 2, right? Absolutely correct. And very simple also. This is going to be 3. Clear? Now, these are the bonds which are formed between the ligands and the metal. And this number of bonds, coordinate covalent bonds, they are known as more precisely, if we say. So that is basically the definition of coordination. So in the next class, we are going to look at the types of ligand. That is very important. Okay? Very, very crucial. The types of reaction ligands and how they get clubbed to the metal atom or ion. So that we will see in the next class. Okay? So let me end the
So
class.
can you show the
Yeah,
coordination compound complexes types? That
yeah,
part. I didn't
yeah,
get it.
exactly. Yeah, you can see. So this is how we started the classification. Okay, and 2 types, double salts, coordination compounds. Here are the 2 types you can see. Within the coordination compounds, uh, first I have explained it in a general way. Then I have further classified them on the basis of their stability. Here, then we moved on to the common terms and representations. So a general way of representing different parts of a compound. And what do we call those parts? The definition you need to be very clear, because they will ask you the definitions, right? So let me end the class. So let's proceed in the next class. Okay. So bye bye
Thank you, sir.
everyone. Good night. Take care.
That's all.
Bye.